Hi everyone, I am Giulia Peveri, and today I'm going to present you work that I've done in collaboration with my supervisor, Valentina Forini, with Lorenzo Bianchi, and with Gabriel Briar. I'm going to talk about a non-perturbative formulation that we proposed for the Mellin transforming one-dimensional CFT. If you want to know more about the proper application of this formalism, I suggest you to look at video poster by Gabriel that it's called Using the Mellin transform in one-dimensional CFT, where it's going to present some of the way to study and to extract CFT data. I will start by briefly motivating why we're interested in one-dimensional CFT. Well, the first reason is, of course, due to the famous ADS-CFT correspondence. So a correspondence between a conformal field theory and a string theory in curved space. And in general, of course, knowing some information on one of the two sides allow us also to understand better the dynamics on the other side. This is a weak, strong duality. We're also interested in one-dimensional CFT because they can be interpreted as defect in higher dimensional CFT, as in this example where we have a line embedded in a higher dimensional space. And this defect can probe some information about the theory that are not really accessible to correlation function of local operator. Moreover, every higher dimensional CFT is a one-dimensional CFT because we can restrict the correlators to lie on the line, and we can impose the axioms of the conformal group in one dimension, which is SL2R. And finally, it's a simpler setting, but it is constraining enough to test some ideas about higher dimensional CFT. But why we want to apply this formalism, the Mellin formalism, into this context? Well, the first application in this case dates back to 2009, and it was done by Mac. And one of the latest development has been done by Penedones, Silvesi, Voyedov in 2019, where they did a non-perturbative definition of the Mellin, but in higher dimension. And throughout the study here, it has been proven to be a really effective description for correlation function in higher dimensional CFT, because it allows us to have a nicer representation, a simpler representation for this correlation function. And it's a sort of Fourier transform, but in curved space. It's also quite interesting because of its similarity with scattering in flat space, and I will show you, as I will show you in a second. Let's review first some basics in CFT1. In a CFT in general, we have two types of players, which are the primaries and the derivatives of the primaries, so-called descendants. And as in every QFT, we can define an OPE, so an operator product expansion. If we take the operator of two, the product of two operators really close to each other, we can express them as a sum over the primaries, which has a finite radius of convergence and a characteristic power law dependence. These two elements that we see here, so this delta and C, are quite interesting and made up what is called CFT data. And in particular, they are the scaling dimension of the operator of the theory, which can be derived from the 2-point correlation function and the 3-point coefficient, because they can be derived from the 3-point correlation function. And they're also called the OPE coefficients, since they appear here in the OPE, but they are also the structure constant of the operator algebra. What's important is that the full knowledge of the CFT data would allow us to compute any endpoint correlation function by reducing them through the OPE, and so would allow us to solve exactly the theory. And that's indeed the main goal that we want to achieve with our Mellin formalism. Because indeed, with this Mellin language, the OPE consequences are translated into simple analytical properties. This means that there is a correspondence between the physical exchanged operators and the poles of the Mellin. Here we see an example where we have expanded in perturbation theory the scaling dimension and these OPE coefficients, and we can extract information of the anomalous dimension, for example, looking at double poles. While on the other hand, looking at simple poles, so the residues, looking at the residues of simple poles and the position, would allow us to extract information about the first order in perturbation theory of the OPE coefficients. Finally, we're interested in cross-symmetry, which is a powerful constraint that we can introduce And so it's an equality between two different OPE channels, the S channel and the T channel. But let's move to the proper definition of our melin, and let's look at the object to the object on which we want to apply it, which is a 4-point correlation function of identical scalars. This is expressed as this f of t, which is a sum. We have the OP coefficients, and this part is called conformal block. So it's a sum over the conformal blocks. In a one-dimensional CFT, we have only one independent cross ratio, which is the only point which is invariant under conformal transformation, this Z, and it spans between 0 and 1. In our particular case, we prefer to use this T, which is a combination, a ratio of the Z, only because it spans between 0 and infinity, and it's more convenient for the definition of melin, which is precisely this one. This is the definition of melin and anti-melin that we propose. In this particular case, you see M hat. M hat is not really the melin, it's called reduced melin. And M hat is just a product of the melin times some gamma function, gamma to delta phi plus A minus S. And in particular, this gamma function needs to be factored out for some application because they carry an essential singularity and infinity, and we don't want it to be on the shoulders of our melin, M of S. So we have parameter A here, and I'm going to comment on it in a second, and S, which is the only independent melin variable in 1D, which of course is equal to, because of course the number of independent melin variable needs to be equal to the number of independent cross ratio, and it's also equal to the number of Mandelstam variables, as due to the similarity with scattering in flat space. And here you see we are doing an integration between 0 and infinity of our f of t, and we have the melin kernel, if we want to call it like that. And then we have our anti-melin, and our anti-melin, it's taken on a particular contour, and this contour needs to separate this two semi-infinite sequence of poles. And it always needs to have this property, to display this property, and of course needs to be inside the region of convergence. In this particular case, it's between 2 delta phi minus delta 0 and delta 0 for the real part of S, where delta 0 is the lightest exchanged operator in the theory. In particular, here you don't see any dependence on A because A is fixed to 0. What happens is that in higher dimensional case, when we change this value of A, so we add some factors of T or we remove some factor of T, the melin transform doesn't change. But in 1D, this is not the case. In 1D, if we vary this value of A, we obtain a new melin definition because there is an ambiguity due to the fact that we only have one melin variable. So it's not trivial to move from the higher dimensional case to this one-dimensional case. We had to develop an entire new formalism for this case. There is another interesting value for A, which is this one. And if you're curious about that, I invite you to ask me in the discussion or to read that in the paper that we'll publish soon. Finally, this melin needs to, of course, satisfy this crossing symmetry. And this is how it looks like for our correlation function, our f of t. And this is how it looks like in melin space. We apply then our definition to the D function, which are just contact interactions. And here you see we have the operators lying on the boundary, and inside we have the bulk, which is ADS2. And in particular, this D function is expressed as an integral over these propagators, this product of propagators, which are bulk to boundary propagators. What happens in perturbation theory is that the lightest exchanged operator is equal to 2 delta phi. So this is the region of convergence for our melin in this perturbative case. And if we take 2 delta phi equal 1, so the easiest case, we get this the simplest D function. And this is how it looks like in position space. And on the other side, we see what it looks like in melin space. And this is quite interesting because we see here two terms. The second term has precisely a pole inside the region of convergence. which is between 0 and 2 for this particular case. And so you need to vanish, and indeed is precisely cancelled by this factor. And what's left are just double poles at the position of the integers, precisely as we expect from this case. We were able to find a closed form to express the Melling of this D function, which is quite interesting because in a position space, there is no closed form to represent D functions. And it has this form where P of delta is this polynomial expressed here in terms of hypergeometric functions. Finally, there is subtleties connected to the non-perturbativeness of this Mellin definition that we want to have. And this was also tackled into this paper for the higher dimensional case. And the subtleties lies in the fact that operators lighter than 2 delta phi can be exchanged. And so we don't have this neat region of convergence, but what happens is that we have an overlap of poles. And so we have these two different types of poles that mix. And so we need to regularize our function at the extremum of the domain. And we do so by subtracting all this contribution from these operators that are lighter, both at 0 and an infinity. So you see between delta phi, delta 0, and delta phi, such that we can integrate those two pieces, and we integrate them separately by separating this Mellin into a segment between 0 and 1 and a segment between 1 and infinity. But of course, we need to add back those operators, and we add them back as poles. This way, we now have a Mellin definition, which is a sum of these two pieces that is defined as a region of convergence, an improved region of convergence. And by iterating this procedure, we can actually define a Mellin which is convergent over all the conformal plane, all the complex plane. And we can also take an anti-Mellin transform. We can also have a proper contour for our anti-Mellin transform, which is going to separate the two types of poles. What is nice about the extension that we did of this Mellin is that is represented in terms of these blocks, which we can call Mellin blocks. And they are really nice because they are a hypergeometric function divided by this delta minus s, which indicates precisely the position of the poles at the physical exchanged operators, which are s equal delta plus k. And so with this representation, we can clearly see where the position of the poles are, and we can clearly and easily compute the residues. And so we can easily extract CFT data by looking at this representation of the Mellin. And so to conclude, I invite you to look at Gabriel's talk to know about some rules and how we can properly extract the CFT data from derivative interaction, for example. And I want to give you a brief outlook on this topic. And so the idea is that we would like to generalize this Mellin formalism, which is not really the trivial extension of the higher dimensional case. It's more a development of an entire new formalism, inherently one-dimensional. We would like to generalize it to endpoint correlation function and unidentical scalars. But we would also like to explore more this flat space limit, and so the link with the scattering amplitudes, and also to try to compute higher loops, not only tree level. And with this, I really thank you for your attention.